Okay, so my name is Krisjanis BLUMS. I am representing Latvia today with my research paper on Aerospike rocket engine thrust vectoring systems. Okay, so now the goal of my project is to create a thrust vector control system alternative for solid fuel Aerospike rocket engines. And now in order to do that, to complete this objective of mine, I needed to first study some rocket science basics. Now, the first thing you must understand about rocket science is Sir Isaac Newton's third law of motion, which says that every action has an equal and opposite reaction, meaning the amount of thrust that a rocket generates is equal to the energy at which it expels exhaust gases from it. Now, once we understand that, we can also start to understand how it is possible to maneuver a rocket during flight. Now, the thrust that it generates by shooting out exhaust gases out of it, it creates a line of thrust or a thrust vector. Now, if this thrust vector is running straight through the center of mass of a rocket, it will fly straight. But if there's an angle by which the thrust vector is offset from the center of mass, the rocket will pivot in the opposite direction. So this is how rockets can maneuver during flight. Now, the next thing that must be understood is how to generate this thrust. And in chemical rocket engines, the way it's done is by accelerating the exhaust gases to a supersonic or a hypersonic speed. Now, in order to do that, you need a convergent divergent type nozzle, which takes first the gases that are produced by the chemical reaction. First, they are subsonic, meaning below the speed of sound. And the nozzle, it converges by decreasing its volume until the point where the gases reach exactly the speed of sound. And at this point, an interesting thing happens in fluid dynamics. Once a gas reaches exactly the speed of sound, then after that happens, you can increase the volume of the nozzle, which will, instead of decreasing the speed of the gas, will increase the speed of the exhaust gases. And this is how rocket engines can create massive amounts of thrust from their chemical fuel and oxidizers. Now, how an aerospike rocket engine differs from a standard bell-shaped nozzle, which you most likely have seen as it is the most prevalently used one, is that on the screen you can see in the picture there on the left side, there is sort of a spike-shaped object in the middle of the diagram on the bottom. Now, what this does is the spike that extrudes out of the outer edges of the nozzle quite a bit, it will continue accelerating the exhaust gases further out. Now, after knowing these things, I had to find a solution to the problem of creating a new alternative thrust vector control system for solid fuel aerospike rocket engines. Now, the solution that I came up with is that instead of gimbaling the engine itself, I decided that it would be possible to change the thrust vector only by gimbaling the spike itself. And the reason why it works, and if we look at this image again, the gases that flow nearest to the spike, they are accelerated further and further, and their pressure decreases. As a gas accelerates, it decreases in pressure, which means that the outside gases are pressed upon it, and it will form a shape that resembles the spike, meaning the exhaust gases will follow the spike and thrust vector as well. Now, in order to test this theory, this hypothesis, there was a necessity for using a rocket fuel. Now, in this case, I didn't pay that much attention to the rocket fuel. The one that was decided to be used was a potassium nitrate and sugar rocket fuel, which is readily available and easy to use, which is why that was the chosen one. Now, Of course, there was also a necessity to create a prototype rocket engine. Now, for this, I wasn't able to do it myself. I ended up getting a sponsor, which it was a company that specializes in metal work. And together with them, I was able to create a schematic that they were able to turn into an actual rocket engine. Now, obviously, there's also a necessity for a way to test this hypothesis. And for this, there was created a test stand device, which measured the sideways oriented thrust, or in other words, the change in the thrust vector. Okay, so in the testing, the photo on the right shows the rocket engine placed upon a test stand, which has the rocket engine facing upwards. And the way it was activated was at first with slow burning fuses, which you can see on the left side of the screen. But later, there was also implemented a system where the engine could be activated from afar by heating up a metal spool from a distance by applying current. Now, during these tests, data that was gathered looked something similar to this. Now, what this diagram shows is change in sideways oriented thrust, or a change in the angle of the thrust vector. Every peak and valley is a change in the direction of the thrust vector. Now, what this shows is that it is actually possible to control the thrust vector of an Aerospike rocket engine only by gimbaling the central spike. Okay, thank you very much for your attention.
Thank you for your presentation. Our experts have any questions? Anybody?
Have you made any prototype of your device?
Yes, the device that I showed in some of those final images was a prototype rocket engine. I also had a test stand.
Yeah, so, and what is the limitation of it?
Personally for me, or for the design itself? I'll answer both questions. For me personally, I don't have the resources to create expensive and greatly capable rocket engines, as I am only a student. For the design itself, there are new technical limitations, so to say. The design from which I took inspiration was one where the entire engine itself is gimbaled. What I changed is that only the central spike is gimbaled. Basically, what that means is that in some rockets, it will be easier to create a system, a hydraulic system, most likely, a gimbal the central piece. And in some engines, it will be easier to create a hydraulic system that gimbals the entire engine. It mostly depends on the rocket itself.
What? Sorry. What angle? What the maximum angle could be corrected using by your method? Because I think there should be more limitations for your method instead of moving nozzles.
Yes, of course. So in the original tests, we were able to create an engine that gimbaled about 2 to 2.5 degrees, which was able to produce about 10 newtons of sideways oriented thrust, which is quite good. In some hypothetical engines that I've dreamed up in my mind and also put on paper, the maximum angle could be up to 10 degrees, but that would be quite complicated and so on and so forth. But another implication of this thrust vector control system would be combining it with a gimbal system that gimbals only the center piece. Let's say, for example, if you gimbal the entire engine, it creates 10 degrees of, you can gimbal up to 10 degrees, and then the central spike can gimbal 5 degrees. You could create an engine that gimbals up to 15 degrees. So it could also be implemented, both methods can be implemented in one system.
Thank you.
Thank you for your
Okay.
question.
Can one question?
We have 1 minute. If
Okay. Thank you. How many nozzle does your engine contain?
Come again? I didn't quite understand.
How many nozzles does your engine contain?
Okay, yes.
2, 3, 4, 5, or more?
In most rocket engines contain only one nozzle. Okay, we must start by defining what a rocket engine is. In most definitions, a rocket engine is the fuel flow cycle, which means in all solid fuel engines where the entire cylinder is filled with fuel, there can only be one nozzle. In some liquid engine, some liquid aerospace rocket, in some liquid rocket engines, it is possible to also have multiple nozzles. But in solid fuel rockets, it's only one nozzle for one engine.
You used in practice your assumptions, and if you used, have you some videos or some results of measurements?
We have measurements. I showed the diagram. As far as videos, I didn't include them in the presentation, but I have recorded some videos of the engine firing.